Welcome back, everybody, for this for the fourth session today, and this will be given by Professor Sarma from ISC Bangalore, whose research interests involve um, examining the electronic structure both experimentally and theoretically, and he will be telling us about electronic and magnetic structures of transition metal oxides.
Thank you, Pierre, for the introduction, and thanks to the organizers in the online Priya and others. I'm sure there's a bunch of people that are helping you organize this wonderful meeting. It's always a pleasure to be back here in this campus, not only in this campus, in this center, which I've been associated in one way or the other from its inception, from the very first year, before it had the campus. And I come often, and it's always very exciting and inspiring to be coming and discussing with various collaborators and friends of many, many years. What I'm going to talk about today, I mean, you have been hearing a lot about theoretical developments, how to understand electronic and magnetic structure. I'm an experimentalist, and what I've tried to do is to give you a very simplified view, a very personal view of how I try to understand transition metal oxides and the particular properties of transition metal oxides that we'll be interested in. We are interested in, as we have mentioned, electronic and magnetic structures. How in very simple terms we can think about them, how we can visualize them, and what are the essential ingredients that we need to think about or keep in mind in order to understand them from this limited perspective of looking at electronic and magnetic structures. That's what I mean. That's my primary affiliation in Indian Institute of Science in Bangalore. I should correct that. It's Bangalore today. I have also secondary affiliation with CSI and NIST in Bangalore, where I visit once in every 2 months or so for some collaborative project. I'm not referring to any funding agency because I'm going to talk about not specific results from our recent work, but tell you more about the way we think about so that it fits into the scope of the workshop or this conference more. But there are several funding agencies that have been supporting us over the years, in particular DST, CRT, and CSIR. Besides all private funding that came from Jamshedji Tata Trust for about 3 years. So basically, of course, I mean, I cannot get into the nitty-gritty details of the electronic and magnetic structures of transition metal oxides. They are vast and very diverse. In order to understand diverse properties, you really need to look at very specifics of the electronic and magnetic structures to understand them. And since I'm trying to understand under one single banner, it is necessarily extremely simplistic view of transition metal oxides. So I'll try to describe to you those common aspects that control the electronic and magnetic properties. But of course, you shouldn't have a very oversimplified view of this subject matter. It's a very, very active and very vast subject matter, and you need to look into the details when you want to answer this specific compound. So that's why this sort of a disclaimer that what we're going to talk about is really broad strokes to categorize and understand in simple terms the electronic and magnetic structures of transition oxides. The scope of this set of lectures, I don't think I'll be able to go through. I mean, this is typically covers electronic structure, magnetic structure, how to investigate electronic and magnetic structure, and if you take studies, this is I've borrowed these slides from lecture series that I've given in a few universities, in Tokyo University and Vienna University. It's a typically 16-hour lecture, and I'm not going to pack that into for you in 1 hour lecture. So I'll just take out some of the more crucial aspects and share that with you today, which is covered most probably. The first one to slightly more elaborate extent, and then the magnetic structure aspect in some less elaborate extent. But why do we want to understand transition metal? That's the very first question one has to answer. I mean, I'm saying let's understand electronic and magnetic structure of transition metal oxides, but one may ask the question, why should we try to understand? What's the interest about it? And so let's start with the simplest transition metal oxide. And a transition metal oxide necessarily, by definition, has two components, of course, the transition metal part and the oxide part. We shouldn't forget that. And the simplest thing that I can do is to take one atom of that and one atom of that and put them together and make a system and look at it. And it turns out, if I restrict myself to the 3D transition metal row, there are many transition metal rows, 5 rows. I'll be talking about them a little while later. In these, the very first row, the 3D row, as we call it, there are many, this monoxide, as we call it, can be formed, TiO2. Chromium oxide, monoxide does not form. There's much good chemical reason. I'll not go into that. But all the other compounds form, TiO2 all the way to C. These are the first row transition metal oxide, the simplest oxide chemical formula for it. They're closely related structures, most of them. And if you ask the question, so what is the electronic property? And at this level, when I'm asking the electronic property, let's ask even a more simplified question, is it a metal or is it an insulator? And it turns out that these two are metallic and these are insulating. Aluminum is, in fact, one of the most insulating materials known to mankind. So it turns out that in a related series, all monoxide, all from the 3D metal, the transition metal oxides, instead of showing a very monotonic trend, as one would expect from periodic table, remember the entire periodic table is established by looking at the periodic behavior or monotonic behavior of physical and chemical properties, but you find violent change of the physical property when you take the monoxides. These are good metals, and some of them are the most insulating substances that we know. So these kind of qualitative drastic changes, of course, pique your curiosity. You want to understand why such a thing happens. This is a plot from Professor Sena Rao's work, very early 1976. You can see what he did again. He looked at the 3D transition metal oxides, titanium to nickel all the way, and the particular variety of oxide that he looked at also had chromium as one of the compounds. And it's a perovskite structure. Perovskite structure is a playground of all synthetic and material physicists and chemists because their properties are really diverse. You can get IT superconductor related to this structure type, colossal magnetic resistance, what have you. I mean, that's really very vast and diverse properties. So in that single series of perovskite structure, where B can be one of these 3D transition elements, LaBO3, something
they haven't turned off. I don't know.
Okay, fine. I mean, I thought it's just timing me on a periodic basis. No, it's okay. So LaBO3, and so I'm talking about LaTiO3 here, all the way to LaNiO3. And what's being plotted, two quantities. This is the band gap in this axis, and this is the room temperature resistivity on that axis. First of all, you can see that the resistivity itself goes through a maximum, establishing in a quantitative manner a non-monotonic behavior when you're going across the periodic table, which right from Mendeleev's time we have been told to expect a non-monotonic or a continuously evolving property.
Sorry.
Yes.
So that I keep track. You just said chromium monoxide doesn't exist.
Yeah, but perovskite LaCrO3 does.
Sorry?
LaCrO3 does. It's this compound, and that's chromium 3 plus.
Okay, sorry.
And monoxide is 2 plus. No, that's a very relevant question, Sumit. It's a good question. I should point it out. CRO doesn't exist, but this compound is talking LaCrO3, and the oxidation state or the charge state of the transition line here is chromium 3 plus. All the transition metals are in 3 plus. The first example, the monoxides are transition metals were in 2 plus state. So the one state actually matters, and that Sumit, you were right to draw attention.
So copper perovskite doesn't exist because it's not there.
It does exist. 1976, it didn't. In a reliable manner, it's difficult to make. It needs high pressure synthesis. Very good question.
Also, in all of these oxides, cadmium and zinc aren't included.
They are not called a transition metal oxide. The definition of a transition metal oxide is where you have more than one orbital, atomic orbital type open, simultaneously occupied, not fully occupied and not entirely empty. And in this series, from going from titanium to nickel, what you have is both D and S occupied. In technically speaking, copper metal will not be, because it's a D10 S1 configuration rather than D9 S2 configuration. You may think of it almost like not a transition metal, but LaCO3 becomes D9. So it's a border like this. Zinc is totally D10. the D level is deep down and you cannot ionize it. So it's not functional. Please feel free to ask questions. We'll stop when the time runs out. Since it's not a syllabus that I need to complete, I don't have to get anywhere. Feel free to ask questions because that makes it even more interesting for me. Okay.
So is that specific reason why chromium 2+ cannot
Yeah,
stick?
yeah. It's basically, I can discuss more with you. It has the problem of the energy level diagram, the chromium D level with respect to oxygen D level gets into such a state that we cannot stabilize the chromium. It will always try to oxidize itself into the chromium 3+. Because chromium 3+,
Of the series, right?
chromium 3+, so what happens is that it's at D4. Chromium 3+ is D3, extremely stable half-filled shell. So that one extra electron, and it has a large spin splitting, spontaneously oxidizes itself. Yeah, from trying to make CO2. CO2 is much more stable. That is the essential.
Just a different approach that is related to something that actually also for the same amount. Probably D4 doesn't exist because D3 is very stable.
That is what I'm saying. That is just exactly what I said. So the half-filled shell of the D3 in this octahedral field, because those are rock salt structure, it will always drive your T2G3 state to be realized, and that extra electron will go to make another T2G3 state. That is okay. So and this other quantity is the band gap, and you can see at that time one believed that lanthanum nickelate and lanthanum titanate both 0 band gap, so they were believed to be metal. Whereas these are insulated, finite band gap. Not only that, the band gap went to a maximum at iron. It took many, many years after 1976, I think it's around 1994, that actually it was shown that lanthanum titanate is actually a small band gap insulator. The reason people believed it to be metallic is that it was very difficult to make that exactly stoichiometric compound O3. It was always O3.02, 03, 04. This 2-3% of oxygen excess, which Professor Rall prefers to talk about non-oxygen excess because the structure cannot have more oxygen, but deficiency of lanthanum and titanium. But the ratio-wise, you can think of it as excess oxygen. Dopes the system, and I'll come to this point later and try to explain to you. As soon as you dope a system of this kind, it should go metallic, and that's why it was metallic. A very small gap. Otherwise, if you can make it proper O3, it's a very small band gap. But it starts with a very small band insulator, becomes very large band gap, and then it becomes small and becomes metallic. Again, a very non-monotonic behavior. And these are the kind of reasons that one believes that, and this is not random, right? I mean, not jumping up and down. There's a systematic behavior which is non-monotonic, which contradicts the periodic table's continuous evolution. And so we think that there must be a generic way of understanding this violation of the expectation and try to understand them. And these are kind of generic understanding that I'm trying to transmit to you the way I understand at an intuitive level without any equation and only using various diagrams. That is what I'm going to try and do. Okay. So, yes.
There is on the y-axis,
Yeah, just what I'm listening.
whose bar is written. What is so? Is it because -2?
Yeah.
Log
So,
rho?
yeah, log rho is -2. It's a decades that are being shown. Oh, whatever I ate for lunch is making me feel very thirsty. Okay. All right. So LaMO3 is what we are looking at. So this titanium is almost metallic. These are all insulating. There's a reason why I'm writing this separately as an insulating, and there's metallic. So almost metallic, insulating, totally, definitely metallic. Drastic changes that have been insisted on and non-monotonic behavior. These are the things that I sort of impressed upon you in these slides. But now let's also look at the magnetic properties, because it's not only the electronic property that I'm interested in, but also the magnetic property, because after all, the electronic property is dictated by the electrons, and so is the magnetic properties. So they must go hand in hand in some way. And it turns out the magnetic properties are also extremely non-monotonic. This is magnetic, these oxides. This has a very complex magnetic structure. These are magnetic, the LaMO3 compounds. These are non-magnetic. This one is non-magnetic, that's why I separated it out. And this is also non-magnetic, but in a different sense. This is non-magnetic in a particular sense. It doesn't have a magnetic moment in the ground state, whereas it has magnetic moments, but doesn't have a magnetic order or doesn't have a local magnetic moment. It has a strongly correlated and hence susceptibility. So the magnetic behavior is also, as the electronic structure, rather complex, seems to vary in a way that's not following a given trend, but demands an explanation. And this is what I'm trying to achieve to the talk that I'm going to present today. Since magnetism is intimately connected to the electronic structure, properties of electrons, so if I have a reasonable understanding of the electronic structure, I must be able to understand the magnetism. That's the hope with which we are approaching. I will talk about the magnetism. I'll come back to it. I just sort of tied them up right now, but I'm now going to forget about magnetism altogether. Spin doesn't exist in our universe for the time being, and we'll only think of electron charge, electron transport, metallicity, and insulation. So let's start with the electronic structure. I need a few very simple concepts before I start to draw the pictures. The concepts are so trivial that you all know about it. An electron, if I want to describe, I need an equation that will describe the electron motion, so that I know what electrons are doing. And you all know this particular equation. Of course, the devil is in here, is the potential energy. And that's the one that I assume through this workshop, much is being discussed, how to calculate the complexity of it and the consequences of that you're being taught. But for my purpose, since I'm talking about a very simplistic approach, all that I'm going to do is to take, which makes life absolutely simple, I'm going to get rid of the complication. Because the entire complication, remember, every electronic problem is defined once you define the potential. And that's also the devil. So get rid of it. Think of V equal to 0. And then I immediately have the solution to the problem. It's a free electron. I know it goes as h bar squared to k squared. So energy is a function of momentum, and that can be shown as this parabolic dependence, nothing but distribution. And I have an equivalent concept, density of states, which tells me in any given energy, in a certain interval, how many states, electronic states exist. And in this free electron limit, I know the solution, it has a square. So I need only the electron dispersion. There's the dispersion relationship, and there's the density of state. These are the two pictures that I'm using. In fact, I've since eliminated many of the slides. I may not even get to the dispersion relationship. We may not even think about it. We'll discuss everything in terms of density of states and try to understand what's going on. So this is the concept that we are keeping. That's the only picture that I'm going to have for the rest of the talk that we're doing. Don't worry about this. This is when these lectures evolved. Pre-PPT era, when I had to do on the blackboard, this was to remind me what I'm going to cover in that, but I'll walk you through the relevant parts. So pictorially, let's try ask the question, what is a metal and what is an insulator? With respect to the picture that I have presented, the density of states. So let's start with a very simple thing. Let's take hydrogen atom. You cannot get simpler than that in quantum mechanics. That's the only exactly solvable real problem, real life problem that we have. Okay. So let's think of hydrogen atom. It has one s orbital, and I'm forgetting about all other orbitals. It has one electron in the 1s orbital that can take 2 electrons. And I'm going to, since I'm interested in solids and not in atoms, atom of course is solid, I don't have to worry about it. But I'm going to put those atoms in a one-dimensional linear chain and ask what its electronic properties will be. So these are either the position hydrogen atom, if you like, or the 1s orbital, if you like, whichever way you want to think about it. And the horizontal line is the energy position, the orbital energy. And for my purpose, and since I have an arbitrary choice of the energy axis, origin of energy is set such that these energies are all zero. So epsilon 0, which is the energy, orbital energy of the hydrogen atom, I set it to be 0. And then I say that, okay, there's a probability that the electron can hop from one side to the other with a hopping probability of T. Then I'll just tell you the result of this electronic structure, which is a very simple type binding model. You can, it's a Mickey Mouse problem. It's a 1-by-1 matrix that you can solve by hand. And as soon as you set up the 1-by-1 matrix, of course, solve by hand, there's nothing to solve. The element that you get is this one. and that's a band dispersion. So that tells you how the energy is a function of momentum, and its T is the Hawking density. And this is the band dispersion. If I plot the density of states from here, from the definition that I did, you'll get the density of states looks like this. Remember, the atomic level energy, I've defined it to be zero. By definition, I said epsilon is zero. In fact, if I set T equal to 0, that means there's no hopping. Then of course, the system will be at that energy, which is the 0. So all states will be here. Entire density of states will be confined at epsilon is equal to 0, if T equal to 0. And since T is non-zero, that density of states spreads out. So electrons can be anywhere with the probability given by this value. These slight roughness that you're seeing is only the accuracy that we have derived. Calculated, it should be smooth in the thing. And these calculations, I think, Priya's student Sumanti had provided me many years ago. I think so, I'm not sure, possibly. Sumanti is here, she should be. Yes, Sumanti? Yes, that's right. So you can close your eyes for a while because it's going to. So this is the bandwidth, and you can see that there is bandwidth. I mean, you can see that cosine function, the maximum value it has is -1 to +1, which means this epsilon case maximum value is from -2t, and cosine is -1, and when it's +1, it's +2t. So it goes from -2t, it's in units of t, from -2t to +2. So the bandwidth is 40, from -2 to +40. It's a very simple tight banding concept that basically the bandwidth goes as 2 into t into the coordination number, which in one dimension, you have two atoms on two sides, so z is equal to 2. So that gives you 40 bandwidth. Oh, that's very simple. How does this bandwidth come out? Can I think of it? I mean, this is thinking in momentum space. K is the momentum space, right? The complementary space. Can I think of it in a real space? How does this come about? There's one way of thinking about it. I mean, just put 2 hydrogen atoms first, then put 2 more, then put 2 more, then put again 2 more. Go on putting till you get very long. If you get very long, you're approaching infinity for practical purposes, because after all, in real life, there is no infinity. So when we are describing in this Fourier space the band structure calculation, and we pretend that something is infinity, we're also doing an approximation. So the idea is, if I keep making it longer and longer, how do I approach this limiting behavior, which is the really infinitely long chain? And we can do that because these are very simple things to calculate. So what am I going to do? Well, solve the problem here. And that's trivial. If you have 2 energy levels and they're interacting with a hopping term of t, it's nothing but you know that you'll get a state at -t and a state at +t, the bonding level and the anti-bonding level. It's a 2 by 2 matrix cyclic equation that you can solve, and you get one solution -t at +t. So if you do that real space sequence of 2 atoms, you get what in -t and one at +t, exactly what we say. Just to remember that if t equal to 0, it should have been there. And if t is infinite, not equal to 0, and if the chain is infinitely long, then it is there. So it's much broader. It's 4t, whereas here the spread is only 2t. So if I go for 4 atoms, what would happen? 4 atoms would look like this. There will be 4 levels. It still looks very different from that. If I put 8 or 10 atoms, you can see that with the 10 atoms, the extrema have reached almost the bandwidth, but it's still very jagged. If I have 100 atoms, then it looks like this. And if I have 1,000 atoms, it's going to look like this, which is not going to look any different from this. So you can see in the real space, as you keep putting these atoms together, those discrete levels are getting more and more in number. They're coming closer and closer. The gap between them is going as 1 over n, or some number over n, 4t over n, the characteristic gap. And when that gap becomes much smaller than the energy scale that you're interested in, often the thermal energy scale, you see the continuum of states and you reach the limit of continuum. That's how the energy states are coming about. And that's how you can think in terms of density of states, relate them to this microscopic hopping between sites that are located and localized in different space. And that's a connection between going from the space to the infinitely long chain. Having understood that part, now let's get back. This we have already understood. Now, hydrogen atom has one electron. One s orbital can take 2 electrons. That means this density of states that I have plotted here, in principle, can take 2 electrons. But we have only 1 electron per atom, and it can take 2 electrons per atom. Which means if I now put in the electrons, all the states up to this point halfway will be filled. And the other half would be empty, because that represents 1 electron per orbital, and there is a 1 empty orbital per site. As soon as that happens, you know that this is the occupied part, and the unoccupied part has a common energy, where there is coexistence of occupied level and unoccupied level at the same energy, with no energy gap. The implication of that you have finite density of states at Fermi energy. That means the electrons can get excited from wherever they are to another energy level. So it will have a spatial dependence which is different, but at the same energy. So you can move the electron without requiring any energy. And that's the definition of a metal. And so that is the way I will think about metal, that when I have 2 states, one occupied, one not occupied, they are exactly the same energy. And moving the electron from this state to the other does not require any extra energy. That means I can move the electron's position with 0 energy being spent, and that's metal. And if I need energy, that means the highest occupied level, chemists will call it the HOMO, and the lowest unoccupied molecular level, or the lowest unoccupied state, in this case, which will be LUMO for a chemist, if they're not at the same energy, which means to move the electron, the lowest amount of energy I must give is to go from here to there. There is no state at this point. Then this is the band gap. And I need to provide that much energy. And so it's an insulator, because I cannot move the electron without giving it this basic amount of energy. And the basic amount of energy, the lowest excitation that I can cause to the system to make the electron move, is the band gap. So that's the definition of a metal, an insulator. And so pictorially, going away from the actually calculated density of states, if I have 2 kinds of states, and here imagine that I have not only 1s orbital, the previous one. So think of this, the 1s orbital, 2s orbital, there would be a band of 2p orbitals. There are different densities of states from different orbital contribution from that side. The hydrogen one, I said it will be exactly half filled and half empty. So that will make it a metal. But so that's a metal, hydrogen atom. But instead of that, if I have another situation which is here, such that it fills completely, that means I have 2 electrons for every 1s level, and that's my helium is going to be an insulator. So the helium atom chain will be an insulator, because helium atom also has 1s orbital, but every 1s orbital will give me 2 electrons. I'll have a density of state that will look like that, and the 2 electrons will exactly fill it. The next energy level available will be the density of states derived primarily from 2s orbitals, and there's a band gap, and I cannot move that electron, the topmost energy electron. I have to move it there before it can be transported to any place, and there's this band gap, which is insulator. So a chain of helium atom is an insulator, a chain of hydrogen atom is a metal. Having answered that, is that okay? And there's also some technical term. We often call this the valence band. That's a conduction band. Basically, if there are 2 bands that I need to consider to understand the transport or any of the physical properties of the material, the lower energy band I will call the valence band, the higher energy band I'll call the conduction. That's the definition. So any other way to make an insulator? So now that you have answered, you can make an insulator with helium, hydrogen, and an insulator with helium. Is there any other way of making an insulator? Can I make an insulator with hydrogen alone? Because just now we have answered that hydrogen will give me a metal, right? Because it has 1 electron, but its orbital can take 2 electrons. So it will always give rise to an 1s derived band itself will be always half filled, because it has 1 electron per 1s, and 1s can take 2. So whatever band structure I do, the density of states will be such, it's half of it will be filled. Can I think of a situation that half filled and yet insulated for a hydrogen atom chain? It turns out that it's easy, though sounds from previous example difficult, but now think of H2 molecules. I'm not going to put them at equidistant from each other. I'm going to make H2 molecules, two of them together, then a gap, then two of them together, then a gap, then two of them together, then a gap. Periodically arrange it such that the interchain is defined by two hopping parameters. One is a hopping parameter that makes the H2 molecule. That will be my T1. And another will be T2, which connects the two hydrogen molecules. When I do that, so there's a T1, and you can immediately see that that will make a bonding level at minus T1 and an anti-bonding level at plus T. Minus T1 plus T1, minus T1 plus T1. And then I have that T2 that connects them. So in an approximate way, you can think, so all the bonding ones at minus T1 will interact with each other with T2, and all the bonding ones at plus T1 energy will interact with other bonding levels at T2. So I have two separate bands forming at one centered around minus T1 with a bandwidth 2ZT2, and another one at the plus T1 centered around plus T1 with a bandwidth of 2ZT2. Does that happen? If I do the calculation, exactly that's what you recover. You can see that -1 minus T, it's in the units of T1. At -1, centered around -1, which is minus T1, you have a piece, then a gap, because that's the large gap. T1 is larger than T2. So this is the bandwidth that's related to T2. There is also 2ZT2, but there is a large gap because T1, which is this one, is much larger than T2. Now you know that this entire thing can take 2 electrons. So 1 electron will go and just fill up this one completely. And then there is going to be this large band gap making hydrogen molecule chain and insulator. So that's a simple way of doing an insulator. Okay? Which is now fine. We understand this. So can I go further than this? Is there any other way I can make an insulator without pairing them up like this? Because I essentially broke the symmetry of the problem from going from the chain, equidistant chain, to inequivalent distant hydrogen molecules.
So why is it called bonding and antibonding?
Pardon?
Why is it called bonding and antibonding?
Good question. What does the word bonding bring to your mind?
They are held together.
Bonding. They are held together, bonding, right? So, so now the bonding is a lower energy level, which is at minus T1. So if, and both the hydrogen molecule atoms give 1 electron each. So those 2 electrons go to this bonding level. So 2 electrons at minus T1. So what is the total energy? Minus 2 T1. Don't worry, you will never be wrong. And even if you are wrong, don't worry. Just give the answer, minus 2 T1, right? Now, if I break this hydrogen molecule, each electron will go back to the hydrogen atoms. And what will be the energy? Each energy is 0, right? 0 plus 0 is 0. And if they're together, then I have minus 2 T1. And you know that energy likes to be as negative as possible. So when electrons go into this level, it bonds the hydrogen molecule. That's why that level is called a bonding level. To put them there, what would be energy? That's plus T1, 2 electrons there, 2 T1, plus 2 T1. From there, it would rather go to 0 state of splitting the hydrogen molecule apart, because that's lower energy. So that's an anti-bonding state. Is it clear? That's right, that's called bonding. So insulator and metal allow me to. Yes, please.
In your previous slide, you
Yeah.
said that when there are 2 hydrogen atoms, then the interaction is T1, and between the molecule, it is T2. But suppose you have a different species between the 2 hydrogen molecules, then can we define it such that way?
You mean, so you are saying? No.
Suppose there is a copper.
Yeah, not copper, oxygen. When you have H2, bring in O. I was just drinking. But we'll not take the drinking analogy far too much into the evenings. So we'll stay with H2O. And so you're saying that if I put an O in between, and then what is your question?
Then can we also define that hopping between O and the hydrogen molecule and this?
Absolutely. Absolutely. You can make it as complex as you want. I mean, if you put an O, you bring in some carbon and other entities, you can do what you want. You can bring in complexity more and more, what I'm trying to do is to tell you what are the basic ingredients you need to look at to understand or anticipate what the properties are. Okay? But definitely you can, I'm staying with H2, but soon I'll have to come back to transition metal oxides. Hydrogen is not transition, not metal, and not oxide. So I'm very far from what I've promised, but these are the preliminaries. Okay. So we have now understood what is an insulator and what is a metal. Very simple. Give me a density of states, fill me up with electrons. If I see clearly the filled states are separated from the unfilled, unoccupied state by what I call a band gap, it's an insulator. But if filled states and unoccupied states, unfilled states reside at the same energy, I have a metal. Wonderful. With that, let me go to the next one. Again, you don't have to look at this, because what we have not said so far, something that is very important, and I hope comes along, is Coulomb. What do I mean by that? Of course, Coulomb energy is all the time there. We're talking about the electrons are bound in one s orbital because of the Coulomb interaction between the nucleus, the proton, and the electron. But that's not the Coulomb interaction I'm talking about. There is some kind of Coulomb interaction that electronic structure theoreticians are always grappling with. It's a very difficult problem. It's the electrons talking to each other. The two electrons, both negatively charged, they repel each other. So as soon, and that is why helium atom is not an exactly solvable problem. You have the nuclear charge, it's interacting with one electron, it's interacting with another electron with Coulomb interaction. If I stopped my interaction there, I can exactly solve this problem because it's nothing but a. But those two electrons are repelling each other. That repulsion, as soon as I take into account, it becomes a three-body interaction, and three-body interactions, even in classical physics, are not exactly solved, and quantum mechanics setting. So when the electrons begin to interact with each other and they're essentially repelling each other, there's some very non-trivial, counterintuitive consequences that I have not told you about so far. And since transition elements are defined by open shells where there are a number of electrons, since I need to have at least two open shells, so I have at least have two electrons that are going to interact with each other, even if I ignore all the core electrons, I cannot ignore electron-electron interaction. In fact, an entire field that a large number of people are very intensely involved in, or the strong correlation science, comes from the fact that Coulomb interaction, when you cannot ignore it anymore, you cannot think of it as an additive, it fundamentally decides the properties of the material that you are going to discuss. And transition metal oxides belong to that class. It's a subclass of that larger class, strongly correlated system, where the fundamental properties that we are interested in, or unique, very spectacular properties, are all somehow connected with this strong Coulomb interaction. The reason that's called strongly correlated physics is very simple to understand. Basically, if electrons are interacting with each other, you cannot have an independent particle picture, because if you try to pull one electron, the other electron also feeds the pull. It's like in a class, if I'm teaching in a class, and if everybody is independent and they don't know that they're each other, or everybody's there, other people are there, I can go and take one student and throw the student out of the class, the others will remain unperturbed, nothing will happen. But if these students are all holding hands, and if I try to pull one student and throw out, everybody will know, and the perturbation will be felt, and the entire system will be disturbed. There's no way of disturbing the system, leaving the rest of the system undisturbed. So the entire system is correlated. And that's the essence of many-body physics. You cannot talk in terms of independent particle physics, and that makes the problem. But we'll sidestep the entire problem and talk about it in very qualitative terms, trying to understand if there's, at the qualitative level, we can understand something of its electronic structure and magnets. That's what I'm going to talk about. But the essential ingredient that I'm bringing in, beyond the orbital energy, the hopping, the filled band, the unfilled band, the concept of a metal and insulator, I'm throwing in a Coulomb interaction between the electrons and asking the question, what would be the consequences of that? Let us see what would be the consequences of that. And there, I'm going to make also a very, very drastic approximation that often physicists don't understand is a drastic approximation, which I'm going to talk about Coulomb interaction as if the Coulomb interaction is not 1/r, but it is 1 or 0. What do I mean by that? If the two electrons are on the same side, same atomic side, they interact with each other. As soon as they're on two different sides, they forget about each other. Life is not that simple. There is always a decay. The Coulomb interaction goes as 1/r. You can have stream Coulomb interaction, what have you. We are going to ignore all the complication. We are going to simplify the Coulomb interaction in terms of only on-site Coulomb interaction. So if the two electrons are on the same atom, they repel each other by an energy U, any two electrons. If I have three electrons, 1, 2, 2, 3, and 3, 1, each of these three pairs repel each other with U, so the total repulsion energy is 3. So now, if you have understood that, have you understood this? It's a simple thing, right? If you have understood that, you have understood the rest of my lecture. There's absolutely no. Of course, think of now T is 0, U is equal to 0. I've called it a metal. All the hydrogen atom energies are at 0. And I can take an electron from any to and put in at any other side. I don't need any more energy because every energy is 0. I can take the electron from the first one and put it on the third atom. It is still 0 energy. Orbital energies are the same. So it's notionally metal. But if T is equal to 0, it has a difficulty in being metal because that wave function of this electron can never go to the third one because there's nothing connecting to it. But if I can give some way, I can pick it up and put it there, then it will not require any energy. So in terms of a total energy concentration, it's a metal. I can have low energy excitations, which are 0 energy excitation. Now I'm going to keep that T equal to 0 part, because we have answered what T not equal to 0 part, what it does. Essentially, it forms bandwidth. Remember, the atomic levels are sharp at that atomic energy, but the bandwidth comes because of the T. So forget about T for the time being, since you have answered. I'm going to switch on U and ask the question what happens. Once I have answered U separately, I'll put the two together to make a picture come. And when I do that, so that's, let's say, let's generalize. I mean, why stay with one electron hydrogen? Because now I'm going to talk about transition metal. Transition metal has D level. D level can go from 1 electron to 10 electrons or 9 electrons. 10 would be boring because it's all filled, but up to 9 electrons. So let's say it has N electron. N is some non-zero number. And then let us ask the question. These are all some transition metal sets. There are N electrons at each site. In hydrogen atom problem, there was 1 electron, so N was equal to 1. But N 1, 2, 3, 4, 5, 6, 7, 8, 9, the same concentration. And I want to make 1 electron go from here to there. That excitation that I talked about. If Coulomb interaction was not there, I said it's a metal, right? Because I don't need any energy. So let's see. So if I move that, what would happen? All other atoms will remain Dn, but this one will become Dn minus 1, and that will become Dn plus 1, correct? And I can easily ask what is the energy of it before. To start with, when this was Dn and that also was Dn, before I moved there, there were M sites. Each site has N electrons. Each of the orbital energy was epsilon. So the total energy was N into epsilon, right? Simple arithmetic, no problem. If you have a problem, please stop me. Now I've moved 1 electron. So now M minus 2 sites have will have N electrons and epsilon. One side will have N minus 1 electron and epsilon, and another side will have N plus 1 and epsilon energy. So the final configuration, when I've moved 1 electron, it has N minus 2 sites with N electrons, that energy. One side with N minus 1 electron, that energy, and one side with N plus 1 electron, that energy. If you sum it up, it's M into N, and it's exactly the same. And that is what I told you, that if Coulomb interaction is not there, you can move an electron from one side to the other with no cost of energy. So that's a metal, because you can have 0 energy excitation in the system. Energetically, it's not for. Now, think that, so that would be, it's down the part. If I now give a bandwidth to the T equal to, so that would be exactly like this situation, that I have a bandwidth. This is the epsilon, the energy, which I have earlier taken as 0, will form some kind of a density of states. It will be half filled, or depending on N, if it was 1 is orbital, it will be half filled with 1 electron. If it is D with a possibility of 10 and you have 1 electron, so the form energy would be here about 1 electron filling, so on and so forth. Those are matters. Showing the Coulomb interaction. Imagine that electrons are. So I'm taking 1 electron from here and putting it there. Now, before I did that, what is the energy? There are M sites. Each of the sites have N electrons. And each of those electrons have an orbital energy of epsilon. But I have pairwise repulsion of n electrons on each side, each pairwise interaction being Coulomb interaction strength U. So this is the net repulsion. Remember I said 3, if you have 3 electrons, 1, 2, 2, 3, 3, 1. This 3C2 is 3. It is just that factor. How many pairs I can form out of n electrons. Each of the pair would contribute an U repulsive energy. I've added that. That's all I've done. This is the common part that I had already before, and this is the extra part. Since there are m such sites, I have to multiply by n. Have you understood this? Then it's a trivial activity. Now take one from here, put it there, and do exactly the same. So now m minus 2 electron sites as n electrons with orbital energy epsilon. Again, this repulsion term. There's one site with n minus 1 electron at that energy, and the number of pairs is n minus 1 C2 with Coulomb repulsion. There's one site with n plus 1 electron, that orbital energy, and n plus 1 C2 pairwise, how many are there? Into U. Just work out that arithmetic, look at the difference, and that's U. Which means one that did not have any gap, zero energy gap, if you have Coulomb interaction, taking one electron from one side to and putting it to another now requires Coulomb interaction energy is equal gap. That means that beautiful density of states that I have drawn with no gap in between, now splits into 2 parts. And there's a gap that forms which is equal to U, because as soon as I now try to move an electron from its lowest energy to another side lowest energy, I need an extra excitation energy of U. And that is a direct consequence. So before I bring in T, which will give the width, I have one energy, let's say this is the ground state energy, and the first excited state energy of moving, the lowest excitation that I can have is U energy above as shown over here. It's like that. If I have finite T, all that will happen is this will broaden and that. And I'm going to show that broadened picture now. When in later talks, which I will not be here in my full, that 6-hour course that I gave, I relate to spectroscopy. Then one can also show that this stuff that I've drawn, which I now am associating with the ground state total energy in a many-body description, and with the first excited state of the total energy in the many-body description, actually refers to the ionization energy and the electron affinity energy. I'm just making the statement. You may not understand, those of you who understand electron spectroscopy, you understand what I'm talking about, but I'll not go into that right now. And this is the bandwidth that forms. That bandwidth, shown by W, is in the order of 2Z. Earlier, it was 2Z. But now the Coulomb interaction, that consideration did not take into account Coulomb interaction. Coulomb interaction will modify this bandwidth. So we say it's in the order of 2Z. Now you see what is the band gap between the two. Band gap is not U. Actually, band gap is reduced by half of this width and half of that width. Both the width being in the order of W, the half of the two widths make it again W. So it's U minus W is the band gap. So when will this material make an insulated to metal transition? If my bandwidth increases or my U decreases such that U minus W by 2 minus W by 2, U minus W becomes 0. When there's a critical U value, when that critical U value is in the order of the bandwidth, then this is occupied up to here. This is totally unoccupied. This point will go and meet that point, and I'll have an energy where the occupied states will overlap the unoccupied states. That means, again, I recover the description, but I can have now low energy excitations without costing me any energy, zero energy excitations. And the system becomes better. So when U is large, I have an insulator. As U becomes smaller, I get into a metal state. Keep this lesson in mind. Because I have now talked about the transition metal. Remember? In the generalization was transition metal. But I have still not come to the oxides. I promised to transition metal oxides. So now I have to bring in the oxides. And that is where one of the questions that came. Now I have to put the oxygen somewhere. Right? So that's one of the, again, forget it. Okay, no, that's okay. So one of the things, what must I change if I wish to talk about the transition metal oxide? I've talked about transition metal, so I have to bring the oxide, which means that transition metal D level I have talked about, but I have not talked about the oxygen. What happens to the D, I've already seen. It gets this splitting. One terminology that I did not introduce, it's not important, but that's how we talk about in slight jargon. The lower band we call upper Hubbard band. The upper density of states that I showed you, or which is the excited state, we call the upper Hubbard band. And that's what happens to the D. It splits into a lower Hubbard band and an upper Hubbard band. What happens to P? We'll make an assumption that P, the oxygen P level, they don't have Coulomb interaction. Why it's justified? Is it justified? We can discuss that, the merits and demerits of those approaches, and we'll think about that at some point. Sumit may be talking about these at some level. Sure. Sumit, will you be covering those? Some of those? Yes, exactly.
Mine is not a tutorial, right?
Yes, exactly. So mine is the calm before the storm. Then you know what happens tomorrow.
I'm the Onahuto person. I was not part of the workshop. I just happened to be.
We are at the right time, at the right place at the right time. Yes, we are fortunate. Okay, so and then we'll assume there are some private jokes. You know, he and I used to play football even before we thought we'll do physics or chemistry or whatever. So we keep pulling each other's legs. So don't U is not equal to 0 here, but we'll set U equal to 0 for that one. Now the main question: where is the P? These states, the oxygen P levels, transition to D level. Oxygen relevant level is P level. So I need to define the oxygen P level, and that means it will introduce a now new energy. I cannot choose everything to be 0. Transition metal energy I chose to be 0. Now I have to, with respect to that 0, I have to define the oxygen. So I need a new energy scale. So that's very important. And then I'm ready to ask, when is it a metal, when it is an insect? I'm not comfortable with my drawings, but I just need to introduce that new energy state because everything else is done. Okay? Particularly because I've assumed the U to be 0 in this case. Okay. So let's get to that. So U equal to 0, oxygen 2p band. No splitting, see? Because U is 0 there. There's no upper Hubbard band, lower Hubbard band. No complication. It's our good old transition, first part, hydrogen chain. And it's fully filled because oxygen 2p6. It's a fully filled level. Now I have to put the transition metal D level with respect to that. I can have a situation that they're there. Why are they split? Coulomb interaction. We already know that. Remember? So the splitting between these two from here to here is U. And that is a band gap. And the other energy scale that I'm talking about is marked here, that is from here to there, is the other energy scale, which is the charge transfer energy. This is something that every chemist knows. How many of you are chemists? Yeah, not a single?
No.
What a shame, what a shame. You and I.
No, so erstwhile.
Huh? Yeah, you and I are the only two. You are erstwhile and I am now.
Erstwhile.
No, we kept the particle conservation. We cross sides.
Thank you, chemist.
Huh?
Manoranjan is here.
Manoranjan is not raising hand. Manoranjan, I have to tell Ram Sesha this. Sorry, yeah, okay. Oh, you have 7 minutes?
You can continue 5, I think.
Okay. I mean, when I begin to miss my audience, lose my audience, I'm
It's 5 and then we have 5:45.
Okay, let me try. Okay, so you see that that's the other energy scale, which is a charge transfer energy scale. Why do we call it charge transfer? It's very simple. What does it measure? Think of an electron from here, oxygen P electron. I want to transfer the charge from oxygen P to transition metal D. What is the lowest energy I can do that? I can take the one that's sitting right up there and putting it right in here. But this is the width coming from P and T. So it is essentially the energy that I need to transfer an electron that is sitting at oxygen P and put it on the transition metal D side. So that's why it's called the charge transfer. Now, the limit that I've drawn in both these, you can see this delta is larger than P. When that happens, then this is of course an insulator because it's all occupied, all unoccupied, and separated by band gap. This limit I know. When does it become insulated? When U becomes smaller than a critical value that we had already seen for transition metal alone. Remember, the upper Hubbard band and lower Hubbard band will overlap with each other. Look what happens here. So if U becomes small, those two will come closer together. They'll overlap with each other. So you will have now the occupied and unoccupied states overlapping at the same energy. Zero energy excitations are possible. It's a metal. It's a D band metal because the Coulomb interaction strength is small. But there is another limit. The limit that here I've talked about is the charge transfer energy is greater than U for both the pictures. But in this picture, U is greater than the critical value of U. And in this picture, the critical value of U is larger than the actual U. So it's a metal that's an insulator. So here actually the oxygen P band is doing nothing. It is the pure transition metal picture that we had before, even without the oxygen, is what is essentially the same. But if I have delta less than U, that would mean that this blob will go and sit in between them because delta is going to be smaller than U. So this gap will become large, this piece will go down there, and this piece will come in the middle. So it will be like something like this. So here the U, this much, this is U, and this is delta. Right? So now the limit is U greater than delta. In this limit, okay, I can forget about U and make it infinity and go. I'm saying that because actually there's an error in this drawing I saw while coming, it's going that way, so I decided to tell you I'm doing the approximation in between. It's the same story that happened whatever the case. So large U. In this limit, if delta is larger than Eg, I have an insulator, but if I have a situation where delta becomes smaller and overlaps that one, then it will become a metal. So keeping U very large as you want, infinitely large, and yet you can make the system a metal by making the charge transfer energy going smaller than a critical value. So there are two different ways you can make a transition metal oxide go metallic, which was not possible. There was only one way that you can make a transition metal go metallic, which was by making U smaller than W. Okay, so this is essentially what summarized in this very famous phase diagram, because Allen Sautsky Allen in 1985. This is the charge transfer energy. It's very complex. It looks like charge transfer energy. This is the Coulomb interaction energy. And what it says that, forget about this shaded part, the rest of the shaded part, this part is large delta but very small U. So this is a metal because the upper Hubbard and the lower Hubbard band overlap each other. This part, you have a large U value is increasing large, but it's a metal because delta has become very small. So the oxygen P band is overlapping the upper Hubbard band. And this is the part where all the insulators are. In this part, where you have the U to be smaller than delta, the gap is controlled by essentially U. So it says U gap proportional to U, not quite proportional, but mainly controlled by U. And the gap, the band gap, is controlled by charge transfer energy primarily in that part. So they are given different names because of that. One is called the Mott-Hubbard insulator. This is called the Mott-Hubbard insulator because this is the way Mott and Hubbard envisage what insulators are in terms of only transition metal D elements, and then the band gap is controlled entirely by the Coulomb interactions. But this introduction of the oxygen P that these people have considered showed that another limit where the band gap is controlled by the charge transfer energy and not so much by U, and that's why it's called the charge transfer insulator. This is called the DD metal because the two upper and lower Hubbard band overlap, both D. Here, the upper Hubbard band overlaps the oxygen P, so the charge carriers have strongly oxygen P character and transition metal D character. So these are called PD metal. There's some work that we had done long time back, and this is the first idea was in 1990 to show that actually you don't have to go to the limit that these people talked about. These people had said that you see that this metallic part starts only when the limit of the P band was here. So they really needed, every time the system became negative delta or negative effective delta, it was becoming a metal. But there are some considerations that they had missed out and which we have done. I'm not going into details of that. Essentially, it's a small twist to the story that brings out something called a covalent insulator, which later, a couple of years later, Fujimori Fruit from Tokyo University, a very dear friend of mine and collaborator, many years, called being negative delta insulator. That means there's a small sliver of in the phase space where you can have the oxygen p band actually overlapping the upper Hubbard band, and if the system, because of strong hopping interaction, can reform into an insulating state. And that insulating state is very important to understand cuprates and nickelates, the later transition elements, and becoming increasingly more important. And this is what we had introduced way back in so this is basically that modified Z phase diagram, where there's covalent insulator, which is also known as negative delta insulator, because you can see that delta is negative here. That Z diagram would have predicted everything on the left of that to be metal. But if you take into account the periodicity of the lattice correctly, you get an insulating phase, and the metallic phase starts at some finite technique. But let me not go into those. So let me not tell you that things can get. So now we are ready to actually answer the non-monotonic behavior. Why? All that I've said can explain the non-monotonic behavior. It can explain because as I go from titanium to nickel, two things that happen, not one. One thing that happens is 3D level is contracting because the atomic potential is increasing, nuclear potential is increasing. And that makes 3D orbitals contract. So the U, the Coulomb interaction strength increases, so U increases. But the same Z increasing not only increases U, but also pulls the D level down. And as D level is getting pulled down, that means that then the charge transfer energy is decreasing. So as you go from titanium to nickel, you should increase U and decrease delta. And in this diagram, so let's start from here. And if I increase U, see, increasing U is to go that way, decreasing delta is to go that way. That means I'm moving in that direction. And as I move in that direction, I can start from very close to the phase diagram. This line measures where the metal goes insulating, and the band gap increases and then again decreases and again becomes better. So it is the opposing trend of U increasing, trying to make it more insulating, delta decreasing, trying to make it more conducting, gives you this non-monotonic behavior of first increasing band gap and then band gap decreasing. From here to here, the band gap increases, then it decreases, and then it's better. Lanthanum nickelate is there, lanthanum titanate is very close to the phase diagram. That's why you got the just to tell you that there can be more complication, just one slide and flash. I'm talking about all the calculations, hard calculations. There's a lot of hard calculations behind, which I'm not going to talk about today. But you know, if you from D9 go to D8, just change one electron. Now we need to bring in yet another energy scale. What is the energy scale? We talked about the Coulomb interaction, the electrons interacting with each other. But now we need to bring in the fact whether these two electrons that are going to interact with each other have the same spin or opposite spin. And that makes an energy difference, which is called the exchange energy or Hund's energy. That for the D9 case doesn't exist. You have only one hole, and you don't have to think in terms of this Hund's coupling strength. But here you need to, and as soon as you do that, if you ignore Hund's coupling strength, J equal to 0, you get a behavior that looks very much like the phase diagram I've shown you before. U and delta, everything here is metal, everything there is insulator. And there's a second order transition from a paramagnetic insulating state to a paramagnetic metallic state. But now make finite J cut, J is equal to 1, you can get that it's an antiferromagnetic insulator, and below this solid line, everything is magnetic. It's a first order transition here. There's a reentrant behavior here. This part is a paramagnetic metal, and there's a sliver of antiferromagnetic. So things can get complicated, so you need to pay attention to the details. And there's just an illustration. I will take another 10 minutes to bring in some concepts of magnetism. Is that okay? Yeah. Is that all right, my young friends? Not that I heard a very emphatic yes, but I'll ask you. Okay? Because you see, I'm used to my voice, and if you talk anything loud, less loud than that, I can't hear. I'm hard of hearing at my age. So, but I'm. So
There should be some question.
The next talk begins at.
Huh?
The next talk begins at 5.
Then I in now and let them ask questions, and I don't have to finish. magnetism, I'll come back in the next year, they will organize again a similar one.
The next talk we can begin maybe 5 minutes later. Can we inform the speaker? So
Who is the speaker?
The speaker is online with a Bhattacharya from Dresden.
I
He's
know.
supposed
No,
to.
because I want to know who's going to be terribly angry with me.
So Prism will be informed. I do have a point to make about your talk.
Sure.
That's why I sum a couple of things.
Okay.
Because I do want to point out something that is missing in bank calculations.
Okay, absolutely. Though I have not talked about band calculation at all.
It's implied that we'll definitely have some spot for the question.
Yeah, sure. Okay, so let me bring in the, again, very simplistic description of how to understand magnetism. Okay, because now the magnetism is there. I'm going to now not talk about the next slide, which talks about if you dope the system, what happens. Because I made a stray comment that if you take this picture and dope electron or hole in the system should go metal. And there are ways of experimentally doping the system with electron or hole. For example, I mean, whether it's this Hubbard limit or this charge transfer limit, if I dope holes, what will happen? I mean, that some of the electrons will go away. I'll have occupied level and unoccupied level at the same energy. And here, if I do, it will be like that. If I dope electrons, it will move in there and there. So the system should become metal. In these descriptions, and ignore the model Hamiltonian calculations of many of these cases. In fact, you'll find the system must go instantaneously at the smallest amount of doping. And I will only tell you experimentally what really in reality happens. Where is that? So these are the compounds. All of them are insulating without the strontium. Putting strontium, and you know that all of them are insulating, I have already told you. Putting strontium in place of lanthanum is putting holes into the system. So the formula will move down. If in this limit, I'm in the Hubbard limit, so it will move into the upper Hubbard band. In this limit, I'm in the charge transfer limit. It will move into the oxygen P level. The metal, the system should become metallic. And what happens is that if I dope these two, it will indeed become metallic. It becomes not metallic for any level of doping, as much as you can dope. This shows metal insulator transition as a function of temperature. This again doesn't become metallic unless you go to 100% doping of strontium, and this becomes metallic, which is all over the place. This is only to say that you don't have to wait to hear what Sumit has to say that is missing. There's plenty of things missing on that make this interfield extremely interesting. And there's a lot more to think, but even these, you can start by thinking about some of the considerations that I've talked about. So I'll, again, this has some, let me know. So let me just very quickly talk about this. This is actually part of a talk that I gave under the title of abstraction of magnetism, but I'll not do it. Okay. So let me, okay. So in order to understand magnetism, now we have to think in terms of the spin of the electron. Now we're going to focus on the spin of the electron rather than moving the electron from one side to the other. Metal and insulator property was related to if I can move the charge. So is there a charge excitation possible, which is zero energy or finite energy? Now I have to ask in terms of the spin's behavior, the moving. What is the smallest building block? Of course, atom. In the atom, I know that the minimum energy configuration is dictated by Hund's rule, which says maximize the spin multiplicity. You have many electrons, parallel, make all of them parallel if you can. Get the maximum spin out of it, and that will be the lowest energy. And that means an atom will have a magnetic moment. I can sum up all those spins together, and I can think of it as with a given spin, which is dictated by the Hund's rule. So atom has a spin, whatever that spin is. And there's an energy associated with that. I already talked about the Hund's energy, which is essentially the energy if I had two electrons, up-down configuration minus up-up configuration. That's my definition of the Hund's energy. So unpaired electrons imply a magnetic moment associated with the atom. That's not yet magnetism, that's magnetic moment on an atom. Now let us ask the question. I have periodic table. I have so many atoms there. How many of them are magnetic? If I ask that question and start coloring for you how many are magnetic, you'll find that there's very few of them are magnetic, and this in the there. Everything else is non-magnetic. And that's a surprise. I mean, there's no rhyme or reason why so few element should be magnetic? Why everything else is non-magnetic? Because all atoms can have the magnetic moment controlled by the Hund's constraint. What happens? Why do we lose the magnets? So the question we are asking, why do so few elements exhibit magnetism? What's wrong with sodium metal? Sodium metal has one electron per s orbital, so it has an unpaired spin, s equal to half. Give me magnetism, but it doesn't. Why it doesn't? These are the kind of questions we are trying to answer. So in free space, if I had atoms that are not talking to each other, each of these magnetic moments would be randomly oriented. Every orientation would have the same energy. And so I'll have a completely disordered, either dynamically or spatially disordered state. So that will not give us really magnetic. All have same magnetic energy. So I'm not going to have a magnetically ordered state. In a solid, of course, I'll have Avogadro number of atoms, many atoms. And if they behave like atoms in free space without talking to each other, then again, I have no preferred direction, no preferred ordering, so I have no magnetism. How do electrons talk to each other? How do they convey to the next atom that what spin I have? How do I tell somebody else what spin I have? This is done by electron hopping, because when electron hops, it's spin constant. And so this electron would try to hop there, hop there, hop there. And this hopping would also communicate with each other what the spin that I'm coming from, and so can talk to each other. Now, talking about the 1s, I hope that's what I'm showing the next. So hopping lowers the energy. Remember the bandwidth 2zt. It lowers the energy by minus z, which is what I gain in energy. And if I have sodium atom and I have ferromagnetically ordered them, you can see each s orbital with one electron. And now you see that in this situation, these hops are not possible. None of these hops are possible because atomic principle will exclude it. Because this s orbital can only take a downspin electron, cannot take the upspin. So if I have a ferromagnetic ordering, then it will completely block hopping. The stability that comes from hopping will not be available to me, which means if I want to make a good metal, I want to scramble the spins up so that I can make it hop from each side to other. And therefore, non-magnetism gets stabilized. If I have very efficient hopping, local magnetic moments will not fall, because in this limit, bandwidth will go to zero, and I don't get the delocalization. So in general, one lesson that we learn, to keep in mind that to gain from the metallic bandwidth, that we intend to destroy magnetism. That's one. We come back to this one. This is the periodic table, which I'll just extract the part which is the transition metal part from here, and if I rearrange them in the so this is a 3D row, 4D row, 5D row, 4F, and 5F partially occupied states. These are all the transition rows. I'm going to rearrange. This is Mr. Mendeleyev's arrangement. I'm going to rearrange in a particular way the periodic table, which will put them like this. And there's a rationale for doing that. This rationale is, you see now I put 4F, 5F, 3D, 4D, and 5D. What I'm doing is the spatial extension of these orbitals. 4F is most contracted. It's very much like the atomic orbital. And as you go to 4F to 5F, 5F to 3D, 3D to 4D, 4D to 5D, the orbitals get more and more extended. And as they get more extended, bandwidth takes over. The bandwidth physics takes over. When it's very narrow, then the Hund's rule physics takes over. The local moment forms more easily. And as I go down this way, the bandwidth physics is going to be more dominant. If I go this way, local moment physics. As I go this way, then also a systematic change I'll expect. As I've already told you, the U I expect to increase this way, so it will localize, give us to localized moment moving in this way. So in this direction and in this direction, localized moment will increase. In this direction and this direction, bandwidth will increase. That means that I can now repaint this one. This part, if I draw an approximate diagonal, these are the parts where the local physics, local atomic moment physics will dominate. Because Hund's energy is large, bandwidths are small. Whereas in the other part of the diagonal, below the diagonal here, the bandwidth is going to control the energy more. Because now Hund's energy is weaker, but the bandwidth stability is large. So I would expect local moment physics to dominate this part and the band formation physics dominating this part and the no man's land being the interesting part, where they don't know whether to go all the way to local moment or to form the band, and depending on partner elements, temperature, pressure, composition, I can tune them and make them go from one to the other, giving rise to transitions between magnetic and non-magnetic states. And that is indeed the case if you recognize what we are seeing: uranium, neptune, chromium, manganese, iron, cobalt, nickel, iridium, silver, not silver so much, cerium, praseodymium, cerium. These are all the systems which show this very unusual behavior, valence fluctuation, magnetism, different valence states, etc. Happens most here. Of course, by making partner elements, you can push these that way or these that way also. But the basic physics comes from. And now, whether it would form what kind of, assuming local moment. Now imagine local moments are formed. And there is some amount of communication, some amount of hopping. I said if hopping is not there, they don't communicate. So let's have some, and if too much of hopping is there, there's no local moment. So let's have the local moments and some amount of hopping. Then what kind of order I can get? I can have paramagnetic where they don't order, they're not communicating enough with each other. I can have ferromagnetic where they all arrange. I can have antiferromagnetic, I can have ferromagnetic. You know about these different structures. But what determines which are the two? Actually, ferromagnetic is fairly boring because there's only one configuration in this lattice that I've chosen. But if you look at antiferromagnet, for example, you can have an antiferromagnet. All these are ferromagnetically coupled, but along the c-axis, these ferromagnetically coupled layers are antiferromagnetically coupled with each other. That's one A type. You can have these lines along the 001 direction, all ferromagnetically coupled, but along the 110 direction, the lines are antiferromagnetically. That's also an antiferromagnetic order. It's a C type. You can have 110 type of ordering. You can see that these are all ferromagnetic, but these are all antiferromagnetic with respect to that. So there's different structure, and that's G type. And sitting over here, or rather from here, you can see that every nearest neighbor is actually with respect to this one. All the nearest neighbor have opposites. That's a G type. Which one is going to form? Why does it form this and not something else? Now it's fine. Well, I'll try to bring it down energetic. And what I'm going to tell you next time will explain to you why such diversity comes. Okay? I'm really sorry that I've gone short of time, but it's good to be curious. I hope you are curious. And you will then try to find out. Curiosity has never killed a cat, and even if it did, you won't look at. So it will be fine. And I have to stop now. Thank you very much. I'm sorry that I overlooked that.
Thanks, Dee, for a very nice talk. So the talk is now open for questions. Hello, thank you. Very nice talk. I have a couple of questions. What is so T equal to 0 was also mentioned of me. And T non equal to 0 was also metallic. Let's say equal 0. So can you explain the difference between these two?
Equal to 0 is metallic in a limited sense. What I showed that the energy required to move the electron from one side to the other is 0. But I'm saying within both, but that there's no way actually the electron can go from one side to the other because there is no hopping. So the wave functions, because T is equal to 0, implies that the electron can never go to the other side. So it's not truly a metal. It's a system which will remain localized but has zero energy excitation that cannot be realized in terms of transport.
But if T is not equal to 0, does it have an incentive to move?
Yes. And now you have, for example, now you have zero energy excitation. The lowest amount of perturbation, think of infinitesimally small potential you apply, immediately electrons will leave. Because now you're defining a downhill. If you don't define a downhill, they can randomly move all over the place. It will explore all the zero energy excitations that are available using the T that allows it to move around. It will be able to do that. But any infinitesimally small perturbation.
But that sounds weird. That it can move around. Which
in a metal, I take a copper metal. I mean, moving around. We have to be a bit careful when you're talking about quantum mechanics. Moving around is not, unless you provide a perturbation, is difficult to describe a movement. A movement has an identity of an electron, a well-defined packet that is moving in time, right? But if you don't have a perturbation, what you have is soup of electrons, the solution to the, I would say, which is distributed all over the place. And there are excitations which are zero energy, which means those states are also superimposed, and they are available at the same energy. So any linear combination of all this degenerate state is also a solution. So if all these degenerate states, and if you prepare different states, you can see it in different states. But you cannot think in terms of a movement.
So more like you can find electron anywhere. So the second question
It's like taking a glass which is full, and it's the molecules are moving around. If you look at it molecules in the classical analog, you'll see the Brownian motion. But unless you tilt it slightly, it's not going to flow. So there can be motion without a flow, and there can be flow with the status.
Second question is, you said popping is conserving the spin orientation. Can we have it not conserved?
Well, I mean, that's it can. I mean, there can be in the hard order terms. I can think of that can also couple to the spin. So you can have processes. We'll still have the T that connects of the same spin state. Other terms in the Hamiltonian that can give rise to spin flip processes, including Coulomb interaction, which means the resulting case can have a mixture of different spin states, not of course.
Like a term where the hopping is actually
Can get, and that happens. I mean, there are many such realizations. For example, again, spin torque aspects. Yeah, we can realize such things. Spin orbit coupled and other situations that can be best. It indeed.
Sir, you have neglected the Hubbard value of p orbitals.
Yes.
Why?
There are some explanation, different kind of explanations exist. I can show you, and in one of our very early papers, I think it is shown also, that at some level you can take the effect of the Hubbard U at some level of approximation, Hubbard U in the P, and dump it in the definition of the Hubbard U for P. It renormalizes the value. In fact, in transition metal oxides, if you ask a question in the atomic level, what is the Coulomb interaction strength in the D level? We'll come to the answer, which is very large, 18, 20 electron volts. But in reality, the Coulomb interaction that you require in this kind of model Hamiltonian matrix to understand properties would be in the order of 3, 4, 5 electron volts. This huge reduction, large part of it comes from the atomic to the solid state polarization contributions. But in that, a part is actually contributed by this renormalization because we are ignoring the oxygen P Coulomb interaction. And if we explicitly take that into account, there will be certain dynamical aspects which we are missing, but you'll see that your UDD will have to be larger. Okay. So approximately it's being taken care of. Then there are other motivations. Most of the time, oxygen P is fully filled. It's a P6. That's the notion we start with. Of course, not in the limit where charge transfer energy becomes small. So the P also begins to empty out. And then it's a more important question. But then again, one can say that I can have a low energy Hamiltonian description, model description, and I have an effective U, which is a single U that will capture, which is the effect of P and D together. So there are different ways of trying to justify. Once in a while, one believes that you need to explicitly take into account the P for certain physics, which cannot be captured.
I have one question. So while you were discussing density of states, for 4 atoms and 10 atoms, all the density of states have same height. But for 1,000 atoms, the height is minimum around E equals to 0 and it's maximum at ±2. So what could be the possible physical reason of that?
The reason actually is simple. When I have very few level, each of the signal that you're getting corresponds to one energy state. And since I'm plotting the density of states, at each of those energy discrete level, I have one state here, one state there, one state there. So all of them the same height, showing that it's one energy state. And then when I'm showing you the 1,000 one, then I'm not showing you all the individual energy levels, because if I draw the 1,000 there, you will not be able to see them. Right? So what I'm doing is what you call the binning, a small window, and counting how many states there are. And this density of states, that's how the equation statement density comes, is changing. It is piling up at the edges, that's why it's high, and in the middle it's low. And this already shows up in the one that I've shown, that if you go from the earlier to later, you'd find that actually there are larger gaps that are developing in the middle when you have finite, let's say 6 or 8. I don't know what are the ones that I've shown here. See? No, it's different. It's not showing here. So basically, here you see there's no state in this particular curve. When I have 1,000, there are less number of states per unit energy. Here, more piles up here. And that's how the infinite one is. So it's going towards to describing the infinite. It's just the number of density of states available in a small window. It behaves that overall shape that you see.
So I have a conflict of interest because the next speaker is an occasional collaborator, but I'm also sitting next to Tanushree, who has worked on negative charge transfer. From my perspective, when you said that you are not doing band calculations, you are, and that has to do with this U. I don't know whether it was U or PP in terms of holes or electrons. Does anyone here know what's the second electron affinity of oxygen? How much energy do you get back
I
by
put
putting in
in
the second electron on oxygen?
must be some, because it tends to go to E6. I don't know how much
The second electron affinity of oxygen is positive.
Okay.
It's
With
9
respect to what?
What?
With respect to what?
With respect to oxygen minus. Electron affinity
Oh,
is the-
oxygen minus.
Yes.
Of course.
No.
But with respect to sodium.
Oxygen 2 minus is actually unstable. You get it back only when in the crystal.
Yeah.
So when you are drawing the density of state, the oxygen p band full and below the copper band, you have done the band theory. It's not true that you have not done band theory.
Maximum potential is taken into account.
Yes.
Obvious.
Yes.
Obviously, maximum potential is part of the orbital energy definition. Otherwise, it won't go.
Right.
That's
But that means there are systems, whatever, depending on the metal, where the oxygen or the chalcogenides are 1 minus, some of the oxygen.
Yeah. Peroxide.
Yes.
The whole
So-
lot of peroxide.
That's what I'm saying, that it was a great tutorial, and I have a conflict of interest with the next speaker by this thing. Also sitting next to Tanushree, and there will be systems in which your oxygen p band will be higher.
So that is showing. You're not paying attention.
That
That is precisely what we showed, and I insisted on that point, saying negative charge transfer insulator plays a very important role. All nickelates and cuprates and higher oxidation state of iron 4+, all belong to this negative charge transfer insulator regime.
I've never seen anybody saying copper oxides are negative charge transfer, but I'm
Oh,
very
well,
happy.
you go and read out it. 1994 paper is with LNCO as the basis.
I'm the next speaker.
Huh? But
I know that paper. I know that paper. I know that paper.
Yeah, please.
Yeah, thanks for the inspiring talk. And well, I have many questions, but let me just advertise that on Wednesday afternoon I will be discussing very similar question. That is when the system can be made out by insulator from very different perspectives.
So those who didn't understand will get it completely
Exactly.
clear.
Okay, I think.
Yeah, we must. Yeah, it's really unfair.
So let's thank Didi again.
Break for 7 minutes.
Yes, some tea also 7 minutes.
No. I think we there is no continue. We continue, yeah.
Speakers will be told that
It's
it's
waiting right now. Let us continue.
5:15.
5:50. I think we are
I
already.
think we are almost.
Because we have something.